Okay, let's have a look at strong and weak acids and bases. Now, we use the term strong and weak sometimes to describe cordial. If someone makes cordial with a high concentration, we'll refer to it as strong. In chemistry, we've got particular terms for strong and weak and different meanings. So when we're talking about strong and weak, we're not directly talking about concentration. We're not talking about how much of a substance has been dissolved into solution. We're actually talking about a particular chemical property of the acids and the bases that we're looking at. So strong means, in terms of acids or bases, that they completely donate or accept protons. What this means is when it gets dissolved into water, so in the hydrolysis reaction where it reacts with water, say we have a strong acid, which we've seen a lot of, which is HCl. If we put this into water, then pretty much all the HCl that we use will go to H3O plus OH minus. Sorry. Cl minus plus Cl minus. So we won't have any leftover HCl where the proton has stuck to the Cl. We'll end up with completely ionized solutions. If we've got a weak acid or a weak base, then we end up with a situation, say we have something like CH3COOH, so ethanoic acid. Okay, our ethanoic acid. This is what we term a weak acid. We use these arrows instead, the equilibrium arrows, and that's because when this happens, we get CH3, COO minus plus H3O plus, but we only get a small amount of these ionized species. Most of it will stay as this protonated form where the proton is being held onto by the acid compound itself. And that's what we mean with strong and weak when we talk about acids and bases. This is how we visualize it. So on the left-hand side here, we have a solution that would be of HCl. We've added HCl to solution and it is completely ionized into Cl minus particles and H3O plus particles in amongst all this water. Okay, so we don't have any HCl that is still together. So we could say this was a 1 molar solution of hydrochloric acid, and we would say it is completely ionized. Therefore, it is a strong acid. In this case, we have the ethanoic acid we were talking about before, which is a weak acid. And because of that, we have the water we had, the same water we had with our HCl solution. Then we have these dots here, which are our anion, the CH3COO minus, which was our conjugate base. This is our conjugate base of CH3COOH, and then the hydronium ion here. But we also have a lot of this species, these small dots here, which is the unionized acid. And what this is saying is that when we dissolve it into water, for a weak acid, most of the molecules will still hold on to their proton. They won't donate it, which makes it a weak acid. It has the ability to donate it, but when we react it with water, so when reacted with water, i.e. dissolved in water, it's only partial ionization. Okay, if we reacted it with a strong base, it would still ionize. But in this case, in the special case where we're talking about when we react it with water, then we're talking about something that will only partially ionize. So I want you to give a definition for a strong acid, a weak acid, a strong base, and a weak base in your notes. This is another way of visualizing it, just because it can be a little bit difficult to come to terms with. So if we call, this is the general form, sorry, my computer's playing up, general form of an acid, okay, which is HA, so this is the proton that can be donated, and this is the rest of the acid molecule. So when it goes into water, we get H plus and A minus in equal amounts. Okay. With a weak acid, we have HA, which is our general acid form. So this is the conjugate base. Oh, it keeps flicking. The conjugate base, and then our hydronium ions. Okay, but with the weak acid, we end up with this still protonated form of our acid mostly, and then only a small portion of our conjugate base. Okay, and we will talk equilibrium again at the end of the year, but basically what this is saying is that only a small proportion will form ions, so we'll have far less ions in solution. Okay, so if we think about that in terms of what that means for an electrolyte solution, okay, remembering an electrolyte solution is an ionic solution where the ions are free to move and carry the current. Because weak acids will have a lower level of ionization, they will not be able to carry that charge as well. So they will have weaker electrolyte activity. We would see a lower current reading in our weak acid than we would for our strong acids. And weak acids will also have a higher pH, so that's these diagrams here. It's referring to the pH that we see of these solutions. Again, because pH is dependent on the concentration of H3O+. So if it's not completely ionizing, then for equal 1 molar solutions, so this would be 1 molar and this would be 1 molar, for equal concentrations, we would see a different level of ionization. Okay, and in this one here where we have 0.1 molar solutions, we can see that the 0.1 molar solution of HCl is 1 pH, whereas of ethanoic acid it's 2.9 pH. And we'll be exploring these properties in practicals in class as well. Okay, so because that of the ionization not being complete, we see this different electrical conductivity and we see different pHs due to the relative concentration of ions. These are examples of strong and weak acids that you need to know. Okay, so generally what we're talking about with weak acids, if we have like 99% of it won't ionize and only 1% ionizes. Examples of these are our ethanoic acid, and then also the way in which CO2 reacts with water to form our carbonic acid and our hydrogen carbonate anion in this case. Strong acids are our hydrochloric acid, nitric acid, sulfuric acid, and hypochlorous acid here. These are all strong acids, phosphoric acid also. So they will completely ionize, giving us those very low pHs and our corresponding high electrical conductivity as well. Strong bases essentially are our metal hydroxides, where we have these completely ionizing in solution. So sodium hydroxide to potassium hydroxide and barium hydroxide, all of which will dissociate in aqueous solution to form strong alkalis. Weak bases are anything with this amine group, like an NH2, and we talked about this in class, anything where it can donate that lone pair on the nitrogen, forming a dative bond to form a positive ammonium ion, such like the NH3 plus water going to NH4 plus and OH minus. So these are our weak bases, anything that contains what we call an amine group. And we'll learn more about that when we do organic as well. Okay, so we have our strong bases, we have our weak bases, and our strong and weak acids. So for strong and weak conjugate pairs, remembering we were identifying conjugate pairs last lesson, the conjugate base pairs following a couple of general rules. That is that a weak acid will have a strong conjugate base and a strong acid will have a weak conjugate base. These same rules apply for acids and their bases and their conjugate acids. Okay, so if we have a general form of an acid, okay, if it is a weak acid, it will have a stronger conjugate base. If it's a strong acid, it'll have a weaker conjugate base. If we have a look at something like that, we said ethanoic acid plus water is going to give us CH3COO minus, the ethanoate anion, plus H3O plus. Okay, so its conjugate base, this would actually be a stronger conjugate base than we would expect. This is a great diagram that you should make sure you put in your notes. These all do have ranges. So sulfuric acid has a very weak conjugate base, and that is the HSO4 minus ion. And you may remember when we looked at this in our last prac, this actually acts as an acid. So it's more inclined to act as an acid when reacted with water than it is actually a base, even though it's an amphiprotic ion. Hydrochloric acid is also strong. Nitrix, our H3O plus, which is our conjugate acid from water, our HSO4 ion. Then we hit our weak acids with ethanoic. Carbonic ammonium ion is a weak acid as well. So this is interesting because where we said we had that rule where the weak base gives a stronger acid, ammonia and ammonium is both actually quite a weak base and a weak acid. And then our H3O and is a very weak base, and then our OH minus. Okay, so just another note on our concentration versus strength. So we've talked about strength in terms of level of ionization, and this is just a reminder that concentration is a matter of the amount of substance dissolved into our solvent. So if we have a look here, we can have a solution of weak acid that is quite concentrated. That is that we have a lot of weak acid molecules in a solution. So in this case, you can see a number of them are still holding on to their proton. Only a few of them have lost it, but there is a large amount of solute per unit volume. Whereas this one on the right, where we have less molecules per unit volume, so there's more space between molecules, it's still a weak acid. So we can have a concentrated solution of a weak acid or a dilute solution of a weak acid. It doesn't change the intrinsic nature of the acid though. It will still stay weak. And then same can be said for a strong. We can have a concentrated solution of a strong acid such as hydrochloric acid, so 10 molar or something like that, and we can also have a dilute solution, 0.1 or 0.01 molar solution of a strong acid, remembering that concentration is always a measure of the amount of particles per volume, whereas strength is talking about the ability for that acid to ionize. Hydrolysis reactions are the ones that we've looked at. It's a reaction where we have the acid reacting with water or a substance reacting with water. So when we write our HCl plus H2O goes to H3O plus Cl minus, this would be considered a hydrolysis reaction. When a compound acts as an acid, it reacts with water to produce hydronium ions, always. And the other thing to remember is that all acids are covalent compounds that are ionizing in water. Bases can be ionic or covalent, but most acids are generally covalent compounds. This is the hydrolysis of HCl that we saw before. HCl is donating a proton, acting as an acid, and then the water is acting as a base and accepting the proton, remembering that HCl is a monoprotic acid. Sulfuric acid, this is stepping through the equations that we've seen multiple times by now, so I won't spend that much time looking at it, but read through your notes and be able to identify each of your conjugate pairs and then the acid and base in each situation. Bases are generally ionic. Okay, and these dissociate. IB doesn't make that much difference between dissociation and ionization. It tends to use ionization for both cases. This is just, however, an ionic compound, so really the term is we're freeing up those ions from the lattice, not making new ions. These are our observable properties that we will see in an experiment later this week. Okay, so our concentration of hydrogen ions, aqueous hydrogen ions, so H3O plus, HCl compared to ethanoic acid, and then the corresponding pH, you can see this is much higher. The electrical conductivity of the strong acid is higher, and the rates of reaction will be generally faster because we have more ions in solution already available to react with our metal, and then the reaction with calcium carbonate will also be fast. When we have a weak acid, we have these slower rates, which could indicate a lower concentration, but that's not the case. In this case, it's a lower concentration of H3O plus due purely because it's a weak acid, so it hasn't fully ionized. Okay, so that's it for weak acids and weak bases. Make sure that you have gone over this, pull your notes together, and then we will do some more practicals in class.